So at the previous video, we talked about isolated singularities, and now it would be useful to look at a more global picture. So the more global picture is the following, that we have a domain and we have a function which is analytic on D, with the exception, let's say for the moment being, finitely many isolated singularities. So these strange points, let's denote them with little circles. And let's say for the moment being that we're talking about A1, A2, A3, A4. So we have 4 points at which the function is not defined. They're everywhere in D it is defined. And we're pretty much want to see what happens in terms of integration, how integration is affected by these singularities. So our main interest lies in simple closed paths. So these are paths that begin at a point, end at the same point, and are traversed in the counterclockwise way, something like this. And there is a theorem that says that such a path divides the plane into 2 components, its interior and its exterior. That's the Jordan curve theorem. And pretty much what happens is that one of the most important theorems in analysis, in complex analysis, in elementary complex analysis, implies that if the interior of the path does not contain any singularities, so if C is a path with no singularities in its interior, then the integral of our function along that path is 0. And in a later video, we will try to justify this. What is really, really interesting is what happens in the case that our path encircles some of the singularities. So take a look at this path, for example. Okay, so let's call the first path was C1. Let's call this path C2. So this was C1. And we ask what happens at C2. And we have a very interesting situation here. The principle that we gave before allows us to pretty much localize the integrals. What do I mean by this? Let me draw a larger picture and explain. So let's say that this is the path C2. And we have one isolated singularity here and one isolated singularity there. So when we want to consider this integral, it turns out that we can think of each singularity being surrounded by a circle, and then we can strategically break this integral so as to traverse a more complex path. So instead of just going like this and traversing the path in a traditional way, imagine that it does something very weird, that instead it, let's say, goes like this, then turns into the segment, traverses the circle in a counterclockwise way, and then comes back on the segment and then continues. Okay, and when it encounters the origin of the second segment, again it goes in, traverses the other circle in the counterclockwise way, and pretty much comes back. So when we look at a traversal of this type, then it's not too hard to eventually realize that and I actually here it may have been useful to consider some other parts. So if, for example, I had introduced two more such things and made the traversal a little more interesting, I would have been able to separate the whole path into paths that do not include any singularities in them. So let me actually color them so that you can see them. So for example, this is a part that doesn't include any singularities in it. And I could think of the traversal of this path as going around the boundary of this. And then let's say you would have this part where you have no singularity. And then let's say you have this part where again you have no singularity. So the only two parts that really matter are the two disks. So it would turn out then that the integral around this path ends up being the integral on the first little disk. Let's call this R1. And the second little disk, let's call this, or circle I should say, call this R2. So in other words, any integral that you may have over a path can be eventually isolated on disks that surround the singularities. And remember that at any singularity, the function is a double-edged power series. So you can look at the expansion around one of those singularities, or let's say around A2, and your function would be something like this. So it would be C naught plus C1 Z minus A2 plus C2 Z minus A3, I'm sorry, A2 squared plus C minus 1 Z minus to the negative 1 plus C minus 2 times Z minus A2, sorry, this A2 everywhere, to the negative 2, and so on and so forth. And it turns out that if you look at these terms and you think that you could write the integral as the sum of the infinite sum of these components being integrated, then each of these components has an antiderivative. The only component that doesn't have an antiderivative is actually this one. And why am I saying this? Because we're integrating over a circle. And when you have components that have antiderivatives, then it will end up being the difference at the endpoints, but the endpoint is the same. So you're subtracting the antiderivative at the same point, and you get zero. So all of these terms here would pretty much give you zeros in integration. The only term that would actually stand out would be this one, which would resemble the integral that we did in a separate video. Remember the integral over the unit circle, which ended up being 2 pi I. Okay, so more specifically, z minus a2 to the negative 1 would end up giving you 2 pi I, and then the only thing that actually stays in there is the coefficient, which is c to the negative 1. So eventually you would get that this integral would end up being c negative 1 times 2 pi I for the first disk plus a similar picture for the second disk. For this reason, we really pay much attention to the coefficient of the negative 1 degree summand in the Laurent expansion, and we call that the residue. So what is the residue of a function at an isolated singularity? It's the coefficient of the negative 1 term if we expand the function as a double-edged series. And actually, it's the only thing that survives the integration that we just described. And so eventually, it turns out that we get the following very, very important theorem, that over a closed contour that is traversed in the counterclockwise way, any integral is equal to 2 pi I times the sum of the residues of the function f of c at the different isolated singularities. So let's call the isolated singularities a sub I. So this sum is over all the isolated singularities. And it turns out that this is an exceptionally strong tool. One cannot appreciate this enough unless you see how many different uses it has, not only from in, let's say, the field that we're studying right now, but this theorem can be used in order to even compute unexpected integrals, such as improper integrals over the whole real line, for example. So let's say you have an integral from negative infinity to infinity, and you expand that function, you consider the extension of this function on the whole complex plane, and you look at a contour that looks like this, a semicircle. Okay, this is the worst semicircle ever drawn, but the bottom line is that you look at such a semicircle and you traverse it in the counterclockwise way, and you use the residue theorem in order to compute the integral over this semicircle. If you're lucky enough, the integral on the circular part, as the radius becomes larger and larger, will tend to zero, which means eventually if you let this expand more and more, you will get your improper integral being equal to the sum of some residues times 2 pi I. And it's really impressive how this can be used in order to compute all sorts of integrals. So we will end the discussion here, and we will try to give some examples in later videos. Thanks for watching.